Okay, in the last lecture, we started to talk about architectures, right? And we learned the two different architectures. First one is a Harvard architecture. In Harvard architecture, as you see in this picture, right, we have two different buses. And bus is the connection between the control unit and the memory. So since we have two different buses, because we have two different memory, I'm talking about physically two different memories, right? One memory is called the data memory, and the other is instruction memory. So all of your instructions are included in the instruction memory, downloaded into the instruction memory, and some of your temporary values go to the data memory. So physically, we have two different memories. Therefore, we have two different buses, and each memory has its own memory space, right? Data memory has its own space. Program memory or instruction memory has its own space, right? So that way, this control unit, it's like this control unit has two different hands, right? If you consider this one as a human, ALU is almost same as a brain, like a body, and we have two different hands. So one hand, you touch some address of data memory, and the other hand, you touch some other place, some other address of instruction memory, right? You can do the same thing, both at the same time. So that's the Harvard architecture. So therefore, you see the concurrent access, right? Meaning the simultaneous access. You can access both things at the same time. So you can do the concurrent access to two memory buses, which means that performance-wise, it's better than this one, okay? So von Neumann architecture has one bus. You have only one bus, and physically, you have only one memory. And inside this memory, you have this much space, address space, right? Address space is from 0 to FFFF, since we are thinking about 16-bit address space. Same thing, actually, for Harvard architecture here, we also thought about 16-bit address space. But in here, we have address space of 16-bit, but out of this 16-bit address space, which is 64K of address space, we divide some part as code memory, another part as data memory, okay? Physically, it's just one, but the address space we divide into two parts, data memory and code memory. And since we have a physical one memory, we have a one bus. So what happened is that this control unit will use some of the address here to access your code and read out the code. And if you need to store some temporary value into data memory, then you have to have a different address and then give that address and put the temporary value in here in data memory, right? So you have to access one by one. So it's slower than the Harvard architecture, but hardware is much simpler, okay? So that's the difference. We also learned the pipelining, right? This is the very important concept you need to understand very clearly, okay? Last year, in the midterm, I think it's midterm, I put a question. One of the problem was that please describe pipelining. And some students say that there are 4 stages. That's it. And he didn't describe each of these words. What you need to describe in pipelining is that you have to describe these words. There are 4 stages, like fetch, decode, execute, write back, and you can do in parallel like this, right? You have to describe all of these things in detail, okay? You cannot just simply say pipeline is just 4 stages, and you expect me to understand what you said, okay? You should not do it. You should clearly explain. I'm not saying this is going to be midterm. I'm saying if this is a midterm, then you need to describe it clearly. Let's look at what it is. What is fetch? Fetch basically means that, let's say you have some program here, okay? Your program is downloaded into here with a binary format, right? Your original code is like a C function, C code. You compile it, make a binary. download that binary here into some other location, right? And the CPU will go there and read it one by one. And read it, this means a fetch. What is a fetch? In English, fetch means go there and get it. That's fetch, right? So fetch is the first step to do. Once you fetch it, then you need to look at it, what it is. Okay? That's decode. It could be add, addition, or it could be multiplication, or it could be any other instructions. So you need to understand what instruction it is. That's decode. And once you decode, now you need to execute. Okay? If that is add, then you need to do addition. Okay? You are actually doing it. And once you do that, generally there will be a result. When you do addition, then there will be outcome. These outcomes should go to a memory. That way, later you want to use it, right? So most of the cases, you have a result. Those results should be right back to the memory. So that's a save. So there are generally 4 stages. And in pipelining, what happens is that you are not going to finish all these 4 stages instruction by instruction. What you do is that you read the first instruction, which is fetch, and then one cycle later, this first instruction now go to the decode stage and look at what instruction it is. At the same time, you can fetch the second instruction. So on the second cycle, the second instruction is here, first instruction is here, right? That's this one. That's this picture. On the next cycle, now the first instruction move on to the execution stage, and second instruction now move to decode stage. Third instruction can be fetched, right? So that's this picture, something like this, right? Those instructions move on every stage. So at a certain point, always your pipeline are filled up with the 4 instructions, right? Because we have 4 stages, right? Ideally speaking, 4 instructions are filled up into 4 stages every time, every cycle. So that's actually the ideal. That's a perfect way of using the pipelining. Okay? Sometimes you have more pipelining stages. Like Intel processors these days, we have more, sometimes 8 or 16 stages. In that case, if things are ideal, then you have 16 instructions filled up in the filled up the whole pipeline stages, right? That's the ideal scenario. But anyway, in that way, by increasing the number of stages, possibly you can speed up everything by executing 16 instructions in parallel. Okay? That's the idea of pipelining. We also looked at Indianness. The concept of Indianness appears when you think about hardware. So from the software perspective, right, you write some value, like a 32-bit value. For example, 89, A, B, C, D, E, F. This is a 32-bit value. Okay? This is one value, just one value. So you define the C function, like int A, you declare integer value, A, right? And A equals to A9, A, B, C, D, E, F. Okay? 0x, A9, A, B, C, D, E, F. In that case, you put this value into variable A, and A is a 32-bit container. And you don't have to worry about how these values are stored in the memory. Generally, we don't care. But from the program, if you are a programmer, then you don't have to worry about. What you need to worry about is write a good program, software. That's all you worry about. But here in this course, we are learning microprocessors, so we need to know detail what happened in the hardware and how these values are written in the memory. Okay? And this is exactly what happened. If you write this value into 32-bit memory, sometimes the value goes into the memory this way, or sometimes go to that way, depending on what Indianness your processor is using. Typically, Intel processor, they are using little Indian, this way. Okay? In other processors, such as ARM processor or maybe 80 or 51. This is some other processor. For example, ARM processor. There are popular processors called ARM processor. Those processors use big Indian. So depending on the processor, they use it different way. Okay? So even though you say A equals to 0x89 ABCDEF, you do that in Intel processor, then the processor will store or write those values into the memory this way. It's inverse way. Okay? So that's a little Indian. So you come up to this issue many times when you do embedded systems. So right now, okay, we really don't care much, but it's really good. It's really important things. So better to remember these things. Okay. Yes.
And are there any advantages of using the Indian or
there's no advantages or there's no difference. It's just a difference of how to order it, how to organize it. No difference, no advantage. Maybe one advantage, if you can, is that the big Indian, it's a little bit easier for us to read because this is exactly the order that I write because my value is this order. Okay, so it's a little bit easier for us to look at. In this case, it's the reversed way. So for us, for human being, for us, it's a little bit, not easy to read. That's the difference. Other than that, there's not much difference. Okay, we also learned some terminology like CISC and RISC. Okay, this is a different architecture. Okay, CISC and RISC are different in the sense that how many instructions they have. In CISC architecture, in CISC processor, they have many instructions. In RISC processor, as it says, it's a reduced instruction set, so it has a small number of instructions. Like this one has like only tens of instructions, but this one has more than 100 instructions, things like that. Okay, so this RISC has only some of the basic instructions. So since we have a small instruction set, hardware is simpler. Simple hardware means the less power consumption. Okay, but in CISC, you have complex instruction set, which means that it has a basic instructions, of course, add, subtract, things like that. In addition to this, it has also some complex instructions, like a complex, very complex, like a MEG. MEG is the multiplication and accumulate. So you accumulate and add, addition, each one of these is a basic instruction, but you put that together and make another new instruction. Okay? That's kind of what you have in the complex set. So this one is a more set because it wants to do the complex instruction in hardware. In this case, you only have basic instructions. So if you want to do complex work, you need to do it in software. You want to do like addition, multiplication, addition. You have to list all that. And so the program is going to be large because you use basic instructions and calculate the whole thing. But in this case, maybe you have some instructions already available in hardware, so you don't have to make the big program. In this case, you can just call one complex instruction, and hardware will do all this complex work for you. In this case, hardware doesn't do it. Hardware is simple. You have to do it using software, writing software. But in this case, hardware do it for you. So it sounds good, but in order to do that, hardware becomes complex, which means that large power consumption. So there's always trade-off. Traditionally, Intel has been using this architecture, CISC architecture, for a long time. And nowadays, the Intel sees that this one cannot go forward because this one has large power consumption. And these days, right, power consumption is really the key technology. Okay, power consumption is really the key. Therefore, they kind of switched into this one these days. So the RISC architecture is more popular these days. There are many other architectures also, but in this course we only cover this one. Later, maybe in the signal processing, in those other courses, we can cover some more details. This is the last picture that we looked at. This is an example of 8051 processor, right? 8051 external memory connection. So here's a picture how you can connect your 8051 processor with the memory. And in this case, memory is external memory, right? It's outside the processor. So 8051 have 40 pins. And out of those 40 pins, we have 4 different input-output ports. In this example, we use 2 ports, port 0 and port 2. Okay? Just an example. And port 0, we use it as AD, meaning A means address, D means data. So the port 0, which is 8 pins, these 8 pins are used for both address and data. Whereas this port 2, these 8 pins are used only for address. Okay? So address, we use 2 ports. Address use 16 pins. Data, we use 8 pins. Okay? Remember that the address space, we use a 16 address space, 64K, FFFF, right? So we need the 16 pins for address. For data, we use 8 pins. But now the problem is that this port 0 is shared by address and data. That's the problem. If you have a separate 8 pins for data, and these 2 are address, then I think that's simple, right? You have a processor and 16 pins connect to the address, another 8 pin data, then it's pretty clear, right? And we have 2 memory, address and data. Then it's clear, but in this case, that's not the case. In 8051, in order to save the number of pins, they actually make the architecture this way. Like this port 0 is shared by address and data. And this is how they use it. Okay? This is the picture recommended by this 8051 chip. Let's see how it looks, how it works. First of all, you have to send the address. Because in order to get the data, you have to say what address I want to read, right? You have to first send out the address. So look at this picture. This is time, right? If you go that way, that's time. So right here, for both port 0 and port 2, we first send out the address. Okay? 16-bit address. From A0 to A7, lower 8 bits use port 0. Higher 8 bits goes to port 2. But if you put these together, it's going to be 16 bits. Okay? 16-bit address goes into both port 0 and port 2. That's what it says, right? At the same time, when you send out the address, what this means is that from here to here, you have an address, right? That's what they mean. At the same time, you have to activate latch. This one is this signal, right? This signal. Address latch enable, right? When you activate this address latch enable, what that means is you turn on this latch. Why do you want to turn on this latch? Because you want to keep this one into latch, right? This value, the lower 8-bit address value, will be stored into the latch, into this latch, right? Because this 8-bit, port 0 8-bit is connected to, these 8 bits are connected to the latch. It connected to EPROM, it connected to RAM also, right? These 8 bits are connected to all of them. Since these are connected to all of them, when you send out 8 bits, these 8 bits goes to everyone. But since we enabled only this one, this one and this one, we didn't enable it, right? See that? It's still just high. This is active low, so high means off, right? It's just high, so it's not off. So you have 8 address, the 8 lower 8-bit here, but these 2 are not turned on, so no problem. but this one we turn on. So this 8-bit now goes to here, into latch, right? And this latch will hold it. Okay? So you hold it here. And then port 2, this port 2 is used only for address. So you can just keep providing the same address. You can actually keep the same information here on the port 2. So you have the same information still go there. And once you have this one, then this address now goes to latch, and latch hold it. Now then you can you can go to the data, because address is already hold, okay? You already hold the latch, already hold the address here. So now we can send out the data, right? Data can go here. And when you send out the data, what you need to do is you now have to enable the memory, right? You want to now enable the memory. So here you see that enable the memory. Enable means that active low. You basically make it low, meaning activate, right? Enable it, enable the memory. So at the time that you enable the memory, port 2 you have address, upper 8-bit address, but port 0 now you have data. Then this memory should get full address, right? So where does this one get the lower 8-bit of address? It comes from latch, right? So latch will provide, now you see the disconnection, right? Disconnection from latch to this one, and also latch to this one. You see that this one is not the connection between these two, okay? This connection actually is, this one is connected to this. This one is connected to this, right? So this one is connected to both. This basically means that this does not mean that these two are connected. These two doesn't have to be connected, right? These two are two different memory, right? Maybe this picture is a little bit confusing. These are not connected. This one and this one is connected. This one and this one is connected, right? So this one goes to here also. This one goes to here also, right? This one also goes to here. So that way, let's say you turn on this one, you activate PSEN. That basically means that you enable this one, you enable this memory, right? Once you enable this memory, then the 16-bit address is coming from here, and data is from here. If you enable this memory by lowering this one, then we want to use, maybe we want to write or read some data here, then this memory is connected with this A pin and that A pin for address, and this one for data. Okay? So from the memory perspective, it has a 16-bit address and also 8-bit data at the same time, right? Since this one, RAM, is read-only memory, it can read or write, right? So depending on reading or writing, you want to activate a different signal. But this one is ROM, so you can only read. So we only have a PSEN. Okay, so now let's move on to today's topic. This picture shows you some of the overview of microprocessor operation. So, you know, the microcontroller and microprocessor is a similar thing, right? You remember that what we discussed about the difference between those two? So we are going to exchangeably use it. So sometimes I use a microcontroller, sometimes microprocessor. I think the microcontroller probably is a better name for this one, but anyway, it's we use one or the other. But same thing basically. So this is what happened. We have C code or assembly code like this. Either one, anyone is fine. But basically, this is your code. For C code, you use compiler. And assembly code, you use assembler. Okay? So for each language, it has its own compiler, right? This is assembly compiler. C language has a C compiler. So once you run the compiler with your program, it becomes a binary like this. Okay? So now we have a binary but this one is actually your code. Okay? Your code is in binary format. And this binary format, now you download it into your code memory. Okay? You download it into code memory. And later, when you power on your board, right, your microprocessor will fetch this one from the code memory. For example, right, in this case, this one is the first instruction. Actually, this one, the nice thing about assembly is that there's a one-to-one mapping. In the C code, you cannot actually have a one-to-one mapping because in C code, when you run the C compiler, right, internally, C compiler will convert your C code into assembly. You know that? The C compiler will not convert the C directly to the binary. C compiler will convert your C program into assembly, and then it automatically runs assembler to convert the assembly to the binary. Okay? That's what they do. But if you go there and write the assembly code directly, then that's good because we have a one-to-one mapping. What that means is this first instruction is actually this one. The second instruction is actually this one. Right? This is like one-to-one mapping. Exactly. And not only that, you see that it's actually move A, and you see the 0, 1 value here, right? And you see 0, 1. And here you see the move 30H, and you see 30. Then what is the 74 and what is F5? We're going to be learning that maybe next week. But that depends on the instruction. This move A instruction corresponds to 74. Okay? And move something A corresponds to F5. We're going to learn that. But what I'm saying is that when you have this kind of assembly code, then you can be assembler. I mean, you can run assembler, of course, but if you know how to convert it, then you can do it by your hand. You can convert each of these into the binary by your hand. Because it's easy, actually. There's a mapping rule. How to convert this one into binary, there's a rule how to do it. Okay? We're going to see it. So you can easily convert it one way or the other. You can convert it from here to here, and if I give you this one, then you can convert it back to the assembly. You can do it by your hand. In fact, that was one of the problems in the midterm, probably last year or the previous year. Okay? So you can do it by your hand, converting. Anyway, so this is the first instruction, okay? And this is the binary format of that first instruction. And now the microprocessor will fetch the first instruction, which is this one. So you fetch it this one. And then microprocessor will decode, right? And once the microprocessor will decode, then 74 corresponds to this one, and 01 is a value. So microprocessor knows that, right? Microprocessor knows the mapping. And then microprocessor will execute it, and the value goes back to A. So this is how things are working. Okay? This is not just an example. It's a simple example. So let's see what happened here in this simple example. Assume that this is an initial state. Okay? Initially, let's say we have all zeros. Okay? Let's say these are registers. A accumulate register and R0 registers, and we have, this is a memory. Okay? 30H, 31H, this is just a memory space, certain memory space. Let's say we have all 0 value as an initial value. Now, when you run this program, as I said in the previous slide, the microprocessor will fetch the first instruction and execute it. And what happens if you execute it? When you execute this, right? What this basically means is that move 0, 1 into A. That's what they mean. What you have to remember is that destination comes first. Okay? Move destination, comma, source. Okay? What that means is move, right? move something from one location to another. That's this instruction. In this particular case, 0, 1 is the value, and you want to move this value into A. So when you execute this one, now then what do you expect? Now you see that 0, 1 in A. In this case, in Windows, right? If you do move, then there was a file here in this folder, and you are going to move this file into another folder, then original one disappear, right? Because you move it, right? But in microprocessor, that's not the case. When you move it, then it's same as copy. Okay, same as copy. The original one's still there. Unless you clear it, it'll be there. Okay, the same as copy. Okay, so if you execute this one, then it's the same as you copy this value into A. So the result is going to be like this. Now we execute the second instruction. Again, we fetch it and decode and execute this second instruction. Now what's happening here? This is source. That's destination. And source is the accumulator, right? And destination is 30H. So you copy value in the A to the 30H. So this is what happened. Okay? You already have a value 0, 1 in A. You copy this one into 30H. Again, move does not clear the original one. Okay? It's the same as copy. Okay? Now you execute the third instruction. Then what happened? Same as the first one, actually, right? The copy the value 31 into R0. So this is the result. And the last instruction, ACH is the value, and put that into this one. But this one, once you execute this one, that's going to result. And the last one, actually, we need to know what this means. This one, right? This one. How do you call this one? At. Yes, right. Just better know. This is a pound. This is at. So whenever you have at, okay, that basically means that you are going to use a different addressing mode. Okay, that's actually today's topic. We're going to learn the addressing mode. Okay, so that's what we're going to learn. So right now let's skip it. But anyway, when you execute the last line, this is the result. Okay, so let's move on. Yes.
In the last line of assembly code, then there is a number of hexadecimal number which is 0AC. And why there is a 0?
That's a good question. Actually, that's covered right here. That's a good question. Okay. Now, let's look at how the assembly instruction looks like. Okay. This is the way of writing instruction, assembly instruction. In this course, we are not going to learn any C language, right? I introduce a C language sometimes in order to help you to understand, but this course we are going to learn only the assembly, okay? Assembly language. So this is the way of using assembly language. First, you're going to have a label, colon, okay? And you have instruction, something like this. And if you want, then you can put a comment, but the comment should be preceded by this one, the semicolon, okay? You put the semicolon, then you can put comments, okay? So this is the syntax. This is how to use the assembly code. So let's look at good one and bad ones here. Let's look at this one. This is your label. Okay? This is just the example, okay? I put the label, my label as a start, colon, and this is my instructions, okay? And this is actually a good example. The reason that I'm saying this good, you can easily see that when you see a bad example. Let's see this is bad example. Why this is a bad example? Because label cannot start with a number. Okay? Label should start with alphabetical letter. You cannot start with a number with a label. Okay? And actually, in fact, in here, right here, you see that first line, first instruction, only the first instruction has a label. Second, third one, fourth one has no label, right? That's okay. Label is not must. You don't have to have a label, okay? You don't have to have a label. But sometimes you need a label because, let's say in assembly language, there is a instruction called the jump. And let's say I want to, sometime here, let's say, you want to jump back to here. Suppose that's the case. Then how can you jump? In order to jump into a certain location, you need to put the label. Only then you can jump to there, right? Using the label. So that's why you need a label. You want to mark it here so that you can find it later. Okay, that's the only way. That's why we need label. But these instructions, you don't have to jump it here, right? Then you don't need the label. Okay? Only when you want to jump to this location, then you want a label.
Professor?
Yes.
So can we put label second?
No problem. You can do it. You can put labels for every line if you like. That's unnecessary, right? But if you like, I mean, that's okay. You can do it. No problem. In fact, if you put labels for every line and you write the code, right? Then what do? You run the assembler, right? Assembler will ignore that. Okay? Assembler will not use it, remove it. So you can put it, but assembler will remove it, so it doesn't matter. Okay, so this is a bad example of putting label. Label cannot start with a number. And this is again a bad example. Label cannot be a instruction. It cannot be a name of the register. TPH is actually name of the register. If you look at the maybe the second lecture, then you see that a list of registers, right? Registers has its own name. DPH and DPL, those are, DP means data pointer, right? Data pointer H, a data pointer high, low, okay? There's DPH, DPL. Those are already reserved. Those names are already reserved for register, therefore you should not use it, okay? Because this is specially reserved for registers. And label cannot be instruction number, instruction name. This is one of the instructions. DJ and Z. J means jump, not, 0. We're going to learn this one, but later. But DJ and Z is one of the instructions. You cannot use the same name in the label. Okay? Other than this one, you can use any label. Okay? Other than this one. Yeah. And let's see. Oh, okay. And not only that, when you write a number, okay, make sure that you put H at the end of it. Only that way it means hex. If you don't put H, then what is it? Decimal number, right? So it's completely different. You have to put H. And not only that, if you have a pound, right? Pound means a direct number. Direct number means that's the number you want, right? Direct number. When you have a direct number, you want to have a pound. When you have a pound, number should be, this value should be starting with a number. Okay? 3, 1, 0, 1, that's okay. But you cannot do pound AC because A is not a number. A is alphabet, right? So you cannot do it. Therefore, you have to use 0. So direct number, direct value, this value cannot start with alphabet. It should be, it should start with the number. That's the answer for that, right? So remember that because this is a if you have ACH, right? Pound ACH, then you can try. You can compile it. Do you have a Kyle assembler, right? Emulator. You can try it. It'll give you error, syntax error, because that's wrong. So you can try if you like. Okay, so this one shows you the structure of instructions. This is another example of our code, assembly code. As I said, in this case, the first line has label and instruction, and I didn't put any comments. If you want to put any comments, then you can put the semicolon and put a comment. This line is for doing this. This line is for doing this. Something like this, right? This is assembly line. And you see that every instruction, every line, we have this structure. So every instruction has this structure. Instruction consists of OP code or operation code, and operand or operands if you have multiples. Let's see an example. Move is one of the OP code. There are many other instructions, but move is one of the instructions. Simple instruction, probably the most popular. Okay, we use it frequently. Move instruction is copying a value from one place to another. But as I said, destination comes first and then source. And these two are operands. Move instruction have two operands, destination and source, right? Because moving is from one to another, right? You need two of them. But so move is OP code and destination source, these are operands. So let's see here in this example, let's see clear A. This is one instruction. Clear is OP code, A is operand. In this case, what this means is clear A means that you clear the value in A. So once you execute this, the value in A becomes 0. Okay, you clear it. This instruction has only one operand, right? Just A, because you want to clear. That's it. So this is simple instruction, right? With only one operand. And move, you need the two operands. Going down here, push. Push is instruction or OP code. 00H, that's operand. This case also you need only one operand. Sometimes, for some of the instruction, you have 3 operands. We'll see it later. Okay, some of the instructions. But generally, you probably have 2. Okay. Anyway, the first one corresponds to OP code, and all the other parameters, those are operands. And every assembly have this structure. Let's look at the assembly language syntax. So I have 3 different examples of processors. Okay. Right now we are using Intel 8051, right? But there are many other processors, tens of processors. For example, Intel 8086. This is another 8-bit processor, but this one is more or less microcontroller. This is more or less microprocessor. You remember the difference? This one, 8086, that is the microprocessor used maybe 25 years ago, 30 years ago. Okay, 30 years ago, if you buy a personal computer, right? Like this one, right? Personal computer, the computer has this processor in it. Okay, at that time it was a 8-bit processor. So this is another processor. And at that time, there was also Motorola processor, Motorola 86000 processor. This is another processor. So these are completely different processor. So what I'm showing here is that different processor have a different assembly instructions. This instruction, right? This is the way used in Intel 8051. If you see another processor, for example, Motorola processor, they use a different way of instruction. You can probably do the same job, but look at this one. They have a MOVE, right? They write it instruction differently. So this assembly instruction is processor dependent. You know, C language is not processor dependent, right? You write the C program, you can compile it into Intel processor, you can compile it into Apple processor, whatever processor you have, right? Apple is not processor, by the way. Apple you can run the any program, any computer, right? C language is good that way. However, assembly language, the assembly language is dependent on the system. Okay, so depending on the processor, you need to write assembly into that way. Okay, so in this course, we are using this processor, so we are only covering this assembly syntax. Okay, but if you're interested and you want to, for some reason, if you want to write an assembly language for other processor, then you need to look at the assembly syntax of that processor. Let's look at some of the categories of instructions. There are several instructions. First type is a moving data, okay, or copying. For example, instruction like move X, move C, push pop, and exchange. Those are the instructions doing this one, moving data from one place to another. Okay? So there's a slight difference for each of them. We'll cover that a little bit later. And there are also other instructions doing logical operations. For example, this one, and you know the logical operation, right? Cross or and not, you know, and rotate and things like that, right? R means rotate, L means left, and things like that. CP, complement, and things like that. We'll cover this one in the next slide. And there are also other instructions like arithmetic operation. Arithmetic operation basically means that you're doing calculation, add C, you know, some of these things. We'll also cover that. Next slide. And there are also the other categories of doing jump and call instructions. Okay, jump. C, NC, B, NB, and BC, all these things are different condition. When you do a jump, sometimes you can do just jump, or sometimes you can do jump only when this condition is met. Okay, conditional jump. There are some of those things. So we'll cover those things. So what you want to remember is that there are 4 different categories of instructions, right? We're going to look at those things. But today, the most important thing is to understand what this means. Addressing modes. Some of you, actually most of you learned the C language, right? Do you understand what pointer means? Okay, someone is smiling, so which means they probably don't understand it. So pointer is very, very important concept. Sometimes I understand that. Sometimes it's not easy to understand, right? But actually, if you learn these things, microprocessor, right? We are not covering any C language here in this course, right? We are only talking about microprocessor, memory, hardware, things like this. But once you understand this one, then now you understand the pointer. We are not covering anything of C language, but you understand this. Pointer in C language is exactly same as one of the addressing mode in assembly here. And that's actually indirect mode, indirect addressing mode. So let's look at one by one. There are 5 different addressing modes in 8051. Okay? First one, before that actually, let's look at the definition of addressing mode. What addressing mode is that, let's say you want to copy one value from this place to another, right? Then you have to specify where is my data, and I want to copy this one to where, right? You have to specify the address, source address, destination address. Okay, that's addressing mode. Simply speaking, okay, that's addressing mode. Okay, so there are multiple ways of doing that. So let's look at one by one. But before that, let's see. The 8051 processor supports actually several physical address spaces. Now you remember that we mentioned the address spaces, right? we have a 64K of address spaces, total 64K. External program memory, that's ROM. We can take advantage of 64K. Okay, we have a 64K of the code memory space. We also have a 64K, another 64K of data memory address. So that's this one. So which basically means that there is a processor here. If you want, then you can buy a 64K memory and connect to and put that into the processor. In that case, the memory is actually 64K and our address space is 64K. So you can take advantage of 100% of address space, right? So that's data memory space. What you can also do is that you can buy another 64K ROM and put that together here also, right? Then you can also use 100% of code memory address space. Okay, so we have instruction memory 64K space, address space. We have a data memory 64K address space. What you see here, on-chip data memory 128 byte, is that this 128 byte is specially designed. Okay, and the address of this 128 byte is already reserved. If you look at our course note from the first lecture, right, then we already talked about this one, right? We already talked about 128 is internal. On chip means internal. Okay, so inside the chip. Okay, we have RAM, 128 byte of RAM inside the memory, inside the chip. That's what this is. But the address of this is like from 00 to 128, the 128, right? So look at those first lecture slide. And this one also, sometimes this one has it, but some other chip it doesn't have it. And also the special function registers, each register has its own address, right? That's in the special function register part. We have 5 different addressing modes in 8051. We need to look at one by one. First, immediate addressing, register addressing, direct addressing, indirect addressing, indexed addressing. Out of these 5, the last one is not that popular. We use that sometimes, but not often. But the first 4 addressings, we always use it. Okay? So we need to know exactly what it is, but it's very simple actually. Let's look at the first one, immediate addressing mode. So as you can see here, immediate basically means that you use the value. Okay? You use the value, not the address in here. Let's look at, you can actually read this, right? But let me explain based on the example. It's easier to look at it. Here, look at the example here. Look at the first line. What I want to do is to copy 01 to A. Okay? That's what I want. But 01 is not address. That's the value. I want to copy the value into A. Okay? It's like A equal to 1. Okay? And 1 is the value I want. So that's immediate addressing. I use the immediate value. So that's why we call this one as immediate addressing. Then how do you know if this one is address or the value? How do you know? We use pound. Here, see the reads pound. Okay? So if you use pound, that means this value is going to be immediate value. Okay? Once you have a pound. Look at the second one, same way. You copy 31H into R0. That's again immediate addressing. I want to put this value into R0. Same way here. Same way here. Okay? In the same way here, I want to copy the value BF into R1. Okay? That's what I want. Same way, on the last example, I want to copy the value 100H into data pointer. But you know the data pointer is 16-bit register. Okay? This is 16-bit at the register, so therefore I use a 16-bit value. Okay? Remember this one. When you use immediate value, you use pound, but the value here should not start with alphabet. Okay? If you want to use with alphabet, you should put 0. Okay? In 8051. Second addressing mode is called the register addressing mode. But this is actually simple. See here, look at the example. You use the register. Then it's a register addressing. Okay? Here, move A R0, which means that you want to copy the value in R0 to A. Copy this one. Okay? You have some value here, and you copy it into A. Okay? The second one is source, right? The first one is destination. So you copy A into R1. Okay? That's what happened. Simple, right? Look at this one. But this copy cannot be done with any registers. See that this mode occurs only between the register A and R0, R7. Okay? You want to copy between these one only. You see that this one is also the copy between these, right? You see that this is not allowed. Okay, this is how the instruction looks like. Okay, you cannot copy between these. That's this one, right? I want to copy the value in R1 into R2, but this is not allowed. This is an error.
That means we are supposed to use
A, yes. If you want to do this, then you want to do it this way. You want to copy R1 into A first, and then A to R2. A to R2, right? That's what you need to do. You have to go through A, because a direct copy is not allowed between these registers. Okay, so that's a register addressing mode. Now let's look at the direct addressing mode. Direct and indirect means the address. So look at here. It's easier to look at the example. So this is an example. You see that we have, actually this instruction is very similar with the immediate one, right? When we look at the immediate addressing. Move A 04H. But the only difference is that we have no pound. Earlier in immediate addressing we have a pound. But here we have no pound. So if you have no pound, that means this is not a value. Okay, this is not value. Then what is it? Address. This is address. So now then what happened? Let's say, suppose that we have pound here, then this is an immediate value. So once you execute this one, A will have a value 04. Because that was the immediate value. 04 goes into A. But this case, this is a direct addressing. We have no pound. So let's say we execute this, then what happened?
the value in G4H goes into
What value goes into A?
the values in 048.
Yes. So 04 is the address. Okay? So in that address, since this is an address, we have a memory, and 04 is the address. In that address, you probably have some value, right? You have a value in that address. That value goes into A. This is a memory, right? Memory, we have a value. This is the address, right? We have a 04H address. Since this is a memory, in this address, we have some value. Maybe 07. Just an example. Okay? We have this value in the memory, in this address. If you do this, right? This value now goes into here. Okay? Whereas if you do this, then this value goes into A, right? Because this is a immediate, this is a direct. Okay? Right? You see the difference, right? So this is a direct mode.
Professor,
Yes.
I just wonder, each address has 8 registers, or registers and addresses are different?
Okay. So look at the first week lecture. Then you see that address. I mean the register has its own address, right? But register is just a memory. Yeah, just other memory. But this is not part of this memory. Maybe we should look at the first week lecture. But look at the first week lecture. We have this is an internal RAM, and inside the internal RAM, remember we have 4 banks, right? 4 bank from R0 to R7, and we have a same like this 4 banks, right? And there are some spaces like a bit addressable, something, right? And there are some area called the special function register. Okay, look at the first week lecture. Then there is a certain area like this, right? Of course, this one has its own address. And if you look at this part, inside here we have a lot of registers. A is here, DP, H is here, B is here, something like this, right? So each register has its own address, right? Special address like this one. But this one is nothing to do with this address. Okay, this one is another address. This one is just address. Address in 04. This is memory. We have a address space of this much, right? So I'm talking about only this address. So the value inside this address is now copied to A. And we don't care where is A. Okay? Registers, we are not using any address. We just say A. And you just simply assume that A is somewhere. A is just container. Accumulator is just container. And that is somewhere. We don't care where it is. Because we just call that A. That's it. Okay? We just simply copy this value into A. That's what this is. And this basically means the second one is what? If you execute the second one, that basically means that the value A, the value in A, is going to be copied into 34H memory, 34H address, right? So we have 34H somewhere here. Now the value in here, let's say we have 08 in here. When you say execute the second line, this value now is copied into here. Okay? So again, this 34H is also address. This is not value, right? This is address. You copy the value in here into this place. This is address, right? So that's a direct addressing. Any question about this one?
If we want to use the register address mode and your addressing mode, we assume that they already have some initial value.
In here, you mean?
Yeah.
You mean this one, right? This one, you don't care about the initial value because you're going to copy whatever value here into this one anyway. So that initial value will be gone anyway, right? But in this case, you're going to copy the value in A into this place. So of course, you already have some good value into A, right? In somewhere up here, you already have a good value into A. You are not going to copy some random value, right? The value in the register may be initialized when you boot up. When you boot up, when you power on, right? Pretty much the value in the register will be reset. Only at the reset time. Only when you reset. But other times, those values are not going to be reset. The only way you want to reset the value in A is to execute clear A. You have to do it. You have to execute clear A, otherwise the value in A will stay there. It's never going to be automatically cleared. Right? Let's look at indirect addressing mode. This is the most important one. Okay? Indirect mode. And this is exactly the same concept as pointer in C. Okay? So let's understand this one. Since we are talking about new addressing mode, okay, we have to use the new symbol. Immediate addressing, we use pound symbol. Okay? Direct addressing, we have no symbol. You just write the address, right? In indirect addressing, we use @ Okay, @ is the symbol for indirect addressing. Okay? Right, so let's look at example here. It's easier to look at example. First of all, in this example, let's execute the first one. You know the first line, first instruction use immediate addressing, right? So once you execute the first instruction, now this value, since you see the pound here, this is immediate value. This 30H now goes into R0. So now once you execute this, R0 will have 30H, 30. Okay? 30H will go into R0. Now let's move to second one. Second one, we know that this one is using indirect addressing mode because we see @ here, right? Since we have @ this is indirect addressing. And now you see that 04, okay? The value in 04. So what is this one, 04? This is direct addressing, right? For source address, this is a source address, you use a direct addressing. For destination, you use indirect addressing because we have @ So now let's see. I mean, just to compare, let's look at this one first. Let's say let's suppose that we have this instruction, which is direct addressing. Okay? If you do this, then now what happened? What happened is we read the value in 04. This is an address, right? Let's say we have 04H here, and we have value, let's say AC. And now, let's say we execute this one. Then what would be the result? AC is now being copied into R0. Okay? Now we lose this value, and AC goes into here. That's the result, right? Okay. Now let's go back. So we have 30H here. Now let's say we use indirect. Okay? Indirect. Then what happened? This same as pointer. So if you understand the pointer, then you see it, what happened. Here's what happened. Source address, it's the same, direct address. So what that means is I'm reading this value, AC. AC is the value that I'm trying to copy. Okay? This is my value. My destination now is indirect addressing. Okay? if that was direct addressing, then I copy this one into right here. But since this is indirect addressing, what I have to do is that I have to go to R0 and read this value. That's going to be your address. That's going to be your target. Okay? So what is the value? 30H. Now this value is copied into here. This is what happened in the pointer. Let's understand what that means. Why do we call this as indirect? Because this value does not directly go to R0, but use this value, right? And this value is going to be now the destination. So the R0 value is not changed. This one is not changed. Okay? The value inside R0 is going to be the destination. So it's like indirect. It's like going here and going back, right? It's indirect. Just to help you to understand, let's look at C language, okay? For as an example. Let's see. Let's say we have a declaration of int pointer C. Okay? Just to compare, let's say we have C, just like this. In that case, what happened inside the memory is that this is some of the memory, temporary buffer, or sometimes it's a heap, or this is like a memory. Okay? In a certain memory, free memory, the compiler will allocate this memory as a C. Okay? So this is C. They reserve a certain memory, like this. Okay? Compiler will do that. And later, let's say I want to have later, if I have this kind of line, then what they do is that they just put this value into here, right? This value goes directly into here. It's like same as immediate addressing, if you like, or we can call that as a direct addressing. Okay, either way. So this is what happened. But now and later, let's say, and now let's say we have a pointer like this. Okay, we have a pointer like this. Then what happened? Now later, then this is a C. Again, in here, in C language, in compiler, when you declare the pointer, what they do is that this is the pointer declaration, and they're gonna have. Okay, here's the thing. There is some of the space, available space, and this C, the pointer C, will point this address. So in other words, when you declare this way, then they're gonna set the first boundary or up, or maybe the bottom address into here. So this one, let's say here is address 88H, and this one has 88H. And now later, when you put some value into here, like some numbers, some big numbers, then this value does not go into here. This value go into here, one by one. This one goes into here, second one goes into here, third one goes into here. So it's like an array, right? You see what I'm saying? That's a pointer. So why do we call this one as a pointer? It's because that this C does not have a value. Okay? This C, the value inside here is not a value. The value inside here is actually a pointer. It's a pointing to an actual location, and this is where you have a value. Your value is actually in somewhere else, right? Your value is some other place. But this place, the address of this place is in here. Okay, that's a pointer. So actual C does not have value. It has address of your value. Your actual value is somewhere other place. Typically, the reason we use a pointer in C language is to use array, right? Or store some big number. If you want only one number, one value, then you don't have to need pointer, right? Just one value you can put in here directly. But if you want to have multiple values, right? Then just C is not enough. So you want to have array, which means that you have to have this amount of memory since you have multiple values. So you put all those numbers in here and use the pointer to point the location. That's how you use a pointer. This is the same way, right? R0 have the value, this value, 30H. 30H goes into R0, but R0 is not used as a value. R0 is the address. So R0, since you use indirect addressing, the value in the R0 gives you and tells you where is the data and where is the destination. In this case, it's destination because in here, right? The value inside R0 will tell you destination address. Okay? So that's indirect addressing. You probably want to do some practice. Right now, maybe looks like you're understanding, but if you go back home, you forget everything. Okay? So go and practice. It's very easy to do it, right? You can, in those Kyle emulator, you can see all the register values, right? So simply write some of the program like this and see what happened in the register and also memory. Okay? You can easily practice. This indirect addressing is very useful. Very, very useful. Last one, actually, here's the addressing. Yeah, the indirect addressing is actually important and sometimes it's tricky to understand. So we have some examples here. So let's see. You can also have indirect addressing to the source. This case, right? You have at the source. In the previous example, you have at the destination, right? But in this case, you have in the source. So what happens if you do this? Think about it. Let's look at it here. Let's say we have R0, and as an example, let's say R0 have the value 10. And now we have accumulator, and also we have a memory. Let's think about two different cases. First is that, let's say we do move A R0. If you execute this one, then what happened? 10H goes to A, simply, right? So this is copy into A. So A is going to be now 10H. But here, what you see is you have at the source. Now then what happened? AC goes into A. Because the value in R0 is not value. This is not a value anymore. This is the address. Okay? So you have to go to this address and read the value from there and copy into A. So once you have this one, then now accumulator has AC. Same way. Here, let's look at this one. If you have no at, okay, A R0. Let's see. Let's say we want to execute this one. What would be the outcome? You mean the addition, right? Addition generally needs 3 values because you want to do A plus B, that becomes C, right? Generally addition is like this. In assembly, what happens is you have a destination and source, and what you do is that you first add these 2 values, and the result goes back to destination. So you add these 2, and the result goes back to here. So the value in destination is now changed. Okay, that's what happened into addition. So let's do that here. Our initial value into A was 0, 2, and R0 we have a value 10. Okay, and you do addition, then what happened? The value in A is now changed to 1, 2H, right? Just addition of these 2. Okay? You simply just add. That's the outcome, right? Okay, now then, as you see here, let's change here. Let's do it this way. I want to change the source R0 into indirect addressing. Now then what happened? AE, right? AE. Because you are not using this one as the value, you're going to use this one as address and go there and read this out, right? And add this one with this, and the value goes to A, right? So therefore, this one plus this one goes to here. Okay, that's what happened in here. Same thing for all the others, right? That's what happened. Let's look at the example 2. Okay. Let's see, one by one. In example 2, we have the direct value, the immediate value, 0, 4 into R1. So now the R1 has this value. Same way, we copy 5, 5 into A, and also 4, 0 into R0. Okay, so this value goes into here, this one here, this one here. So this is like immediate addressing. So we simply just copy the value, each of these value into registers. Now look at the 4th instruction, 4th line. We use indirect addressing for destination. So now let's see what happened. What happened? First of all, source is A, just A, right? So we're going to read the value in A. A has the value 5, 5. And that value will be copied into destination. And my destination is using indirect addressing. So where is this copied to? 40. Yeah, address 40 will now have this value. Okay, this value copies to 40. Address 40. Right? That's what happened here on this line. Next one, INC, meaning increment. You increment the value. Then what happened? R0 has the value what? 40. Okay, R0 has the value 40. But now we want to increment. Then R0 now has value 41. Okay, the value in R0 has been incremented to 41. And the next line, DJ and Z R1 repeat, meaning that this is jump. Okay, DJ. This one we're gonna cover probably next week. But this one simply meaning this one is jump. But when you do jump, you have to say where to jump, right? And in this case, you see that this one is jump to repeat. This is why we need the label, right? You say jump to repeat. And where is the repeat? Here. I put the label here, right? This is why I put the label. All the other, I don't need the label, right? Because I don't have any reference. But this one, I have a reference. Only that way I can jump into there. So I have a label here, repeat, and I jump to repeat. So here, when you see this, then we jump back. Okay, we jump back to this one. And then you have to execute this, right? Then what happened? You execute this again, then what happened? The value in A has never been changed. We have the same value A here. And the value is going to be 55. We still have the same value. But you see that we incremented R0. The value in R0 is now changed. And that's the destination. So what happened? The value 55 is now copied to 41H. Okay? So you incremented the memory, and you just copy 55, and the next loop, you copy 55 into next address, something like this, right? That's what's happening in this example. Okay? Last one is index addressing mode. This is not that popular, but this is pretty much the example that you can use this addressing mode. First of all, you see the move C, which is a new instruction, but move C, and there are also move X. Those are same as move. Okay, MOV. We have we have those three move instructions. This move, the first one, we always look at it, right? This move is like a copy into the internal, between the internal memory. How do you know? Let's look at anyone. Look at this one. We have a move, R1. R1 is a register. Register definitely is an internal memory. Right? You have a register inside the memory, inside the processor. 04, this is immediate value, but let's look at this one. Again, A is a register, it's internal. 40H, 04H, this is the address, but this address is just like 8-bit address, right? 04, that's 8-bit. So definitely this is internal address. So when you copy between the internal memory, internal registers, you use move, simply. But how much is the addressing space? For us, we know that we have a 16-bit addressing space. Okay, total 16-bit. But that's the external memory. Okay, we have a processor here, and we have a 16-bit of address space. Okay, if you want to buy a 64K memory, external memory, and put that together, then you can take advantage of 64K address space. But that's external memory. Okay, external. Now, sometimes you want to access the external memory. Since you put the 64 external memory outside, sometimes you want to go there and read the value from external memory, right? Or maybe you want to write some value into the external memory. So there's some read and write from the external memory. In that case, you have to use this one. Okay? Move C. means C means code. So this is code memory access. X, this means the data. Okay, move X is for accessing the data memory. So if you want to access the code memory, move C. If you want to access the data memory, you use move X. But now you have to understand the difference between these two. The same thing is that this one and this one is simply copy the value from one place to another. In that way, it's the same. So function is the same. They are doing the same job. But what is the big difference? Difference comes from the addresses. Here, in this move, your destination and source, these are the internal memory. But this one, move C, and also move X. In this case, you can use external memory. If you like, let's say move X. In this case, right? Let's say we want to read some value from the external memory. Read it from that. Then the value in the external memory is going to be the source. And you copy it into my internal memory. So my destination is internal. In that case, source is going to be external address. Destination is going to be internal address. Internal address is going to be 8-bit, but external memory, external address is going to be 16-bit, right? This is 16-bit address. In that case, right? Let's say I want to write some value into the external memory. Okay, that's the write case. Okay, I want to write something. In that case, my source address is internal memory, and I want to read it from registers and write the value into the external memory. In that case, my destination is going to be external address. So in that case, this is going to be 16. That's going to be 8-bit, right? Sometimes you want to do copy between the external. I read the value from the external and copy it into another external address, right? In that case, both of them will be 16 bits. Okay? So that's the difference. In move C, this is a code memory. In code memory, you cannot write. You can only read, right? Because that's code memory, that's ROM. So therefore, in move C, you read the value from external memory, that's source address, and copy it back to my internal memory. So source is going to be 16-bit. This is going to be 8-bit because you only read it, okay, from the external. So the message here is that this move is to copy between the internal memory or registers, but move C and move X, you want to exchange the value between the external memory. So therefore, you have to use sometimes 16-bit address. Okay, that's the difference. And look at here. This is a move C. Okay. Copy the byte in the code memory to A. That's what happened here. So I want to read something from the external memory and copy that into my internal A. That's what happened here, right? But think about that. When I try to read some value from the external memory, sometimes I just simply go there and read just one value, maybe. But most of the cases, what happens is that you go to the external memory and read it, and then you go to the next address and read it again. Think about the instruction. You have so many instruction lines. So you read it one by one, right? You just keep reading it. You just increment the address and read it. Increment the address and read it. Read it, right? In that case, you can use this kind of addressing. Okay? If you use this kind of addressing, what happens is that you have a data pointer. Data pointer is the address. Okay? This one has the address. But this is the address of your base base address of your code. Okay, so from your, let's say your code, this is the address, this is a memory, code memory. Let's say your code is from here to here. Then for data pointer, you set it to this address, base address. And then in A, you have the value 0 initially, and you basically you simply do loop. And inside the loop, you keep incrementing A. Okay? Then what happens is this is a base address, and you keep increment A from 0, 1, 2, 3, something like this, right? Then since you add it together, this is a base address, you added the value in A. So for example, base address is like 100, and initially A has a 0. On the first loop, you add these two, it's going to be 100. But on the next loop, this is going to be 1. So when you add it, it's going to be 101. Next loop, 102, 103. Okay?
Then how can you figure out the end of the
In this case, how can you figure out when we finish? Again, this is a loop, right? Loop. Here you say this is a jump. So I said that you are going to jump to this label, repeat. So whenever you reach here, you jump back. Whenever you reach, jump back. So is it like an infinite loop? Sounds like an infinite loop, right? But that's not, because it has a condition. And what is the condition? When this one is not 0. Okay? That's why we see the jump not 0. Okay, we'll cover that next week, but this is the condition. When the condition is not 0, then you jump. Which means that sometimes when you keep incrementing it, right, R1 can go to 0. Then that's the time you finish. Okay, so there is a condition, of course, right? Same way here. Definitely you need to have a condition, otherwise it's going to be infinite loop. So typically when you have instruction, at the end of the instruction you have a null character. We call that as a null terminated. So when you see null, that's the time you terminate it. That's the time you finish. Okay? Anyway, so that's how you do it. This one, it's basically the same. PC, what is a PC? PC is a very special register. It's called the program counter. What is a program counter? Maybe we can look at this code. Let's see. This is our program, assembly program, and I use the assembler to convert this assembly program into binary. Okay, and this binary will be downloaded into code memory, and now we have code memory here. Okay, this is instruction memory, and this one is downloaded into here. Okay, let's say we have these things, 7401, something like this. Okay, we have these things. Let's say address of this one. Okay, the first instruction has the address of 100H, just the example. Okay, and the last instruction is like 110. I'm just an example. And these two are the first instruction, and the second instruction is F530. That's the second instruction, and second instruction is in 102H, okay, and so on. Now what happened is that when you run this code, then microprocessor has to go there and fetch, right? We have to do fetch. Then how does microprocessor know where to go and fetch? We have to go there and read this one first, right? But how does microprocessor know where to fetch? This is the address to fetch. So how does microprocessor know this one? microprocessor will look at PC, program counter. Okay? This program counter, in this example, right? The program counter will tell you where to go and fetch. Okay? In this case, it has the value 100. So the microprocessor will first look at the PC, the value in the PC, and then use this one as the address and go there and fetch it and execute and decode and execute and then write back and move on to the next instruction. So when the microprocessor read this one and go there and fetch, as soon as you fetch, okay, as soon as you fetch it, this one is automatically incremented into next instruction because you already fetched, right? You already fetched the first instruction. So therefore, the value in the program counter will be now moved to the next instruction. Do you understand what I'm saying? So that way the microprocessor next time when the microprocessor fetch it again, then I have to come to here, and this is the next to fetch. Next thing to fetch, right? I have to fetch this one, right? If this one stays 100, then microprocessor will fetch this one again and again and again. You should not do it, right? Since you fetch it already, this one is automatically incremented 102 so that in the next time you read this one and fetch this one. And once you fetch this one, again this one is incremented to the next instruction, you fetch the next instruction. So program counter basically tells you which instruction is going to be the next. And where is it? That's included in the program counter. Question?
Instruction is assigned in that register. So instead of fetch, we use that register, right?
The program counter does not have instruction. This one has the address of the instruction.
That is assigned in this instruction. So I mean, it is not that assigned in that we call about instruction in that order.
You mean assigning means?
One or two means instruction.
This is not instruction. This is the address of the instruction. This is the address, right? We have an address here. So microprocessor will look at the program counter and find out the address. Okay, this is the address. And then go to that address and fetch it. And once you fetch it, then you automatically move on to the next instruction. Okay, the address is increasing. So if you look at the program counter, then you know which instruction you are now executing and what is the next instruction to fetch. That is included in the program counter. Okay? You want to remember those things. And easy to know these things is that you use the emulator, Kyle emulator. You try the assembly language, right? You can easily see those. That's it. Any question?
How close to the address in the PC?
How you can copy that?
Points to the initial address.
Yeah. How you can put the value in the program counter? That's actually done in your assembly. The assembler will do it. So how they do it? That's actually not in here, but here, right? Okay, let's briefly look at it. When you turn on the microprocessor, right? Initially, when you boot up microprocessor, your microprocessor will start from 0000H. Okay? That's the basic address, right? The lowest address, 000. That's the first address. You start with the microprocessor. In that case, microprocessor will start from 0000, right? But your code cannot be in here. For every microprocessor, your program is in somewhere else. Your program is in here. Okay? And there's nothing in between. But your microprocessor starts from here, and address is always incrementing. If you start from 0, 0, 0, 0, then you have to move on to 1, 2, 3, something like this, right? But here, there's nothing. So how can you go there? This is where your code is. So what happened is that for every microprocessor, in your assembly code, what you have to do is that in the 000H, you have to say jump. Jump to this place. And that's why I put the label start. This is my program. I have to put the label start at the first line. Why? Because I want to do jump start at the 0000. Okay? In the 0000, I have to put jump start. And start is my label. And this code is actually here. Right? And my first instruction is here, start. So when you power up, you start from here, and this one is a jump, so suddenly jump to here. And once you jump, then this one is now changed into this value. Start 1,000 maybe. If this is 1,000, then it jumps to 1,000. And then later, then you go to 1,001, 1,002, things like that, right? That is automatically done by this. Okay?
So when I make a new program, then I am supposed to.
You have to do it. Yes. Yes, you have to do it. I'll show you the examples, some of the examples later, but you have to do it. Yeah, it's not automatically done. Nothing is automatically done. You have to do it. Yeah, even this one, right? Jump to start, you have to do it. Okay, see you next week.